All right, I'll give up.
Okay. Do you want to talk about this?
I do. It's a very interesting thing to talk about. Um, so the overall thing we want to do here is derive the naturality um, uh, of fully parametric uh, uh, um, what should I call it? Um, so when you have a natural transformation, you want to be able to say that if it is well, uh, a natural transformation will be natural. Is basically the fact that we want to use if the natural transformation is, or if the transformation is written in a fully parametric style, that is, it's written in such a way that it doesn't examine types at runtime, which it cannot do if it is made up of the set of primitives that Sergey has talked about before. Then you'll get the naturality law, which basically says that if you apply the transformation and do an F-map, then you get the same result as if you do an F-map and then the natural transformation. And so the steps here involve first understanding what F-map and its contravariant equivalent C-map actually do. And then and we'll see that those the definitions of F-map and C-map are they are completely determined by the structure of the type that they are defined for. But we will see that trying to establish parametricity using those as functions is it's too difficult. So it turns out to be easier to generalize the statement of parametricity from functions to relations. And that gives us something that is easier to work with. And then at the end, you can re-specialize the naturality proof defined on relations to functions and get the desired property. So it turns out that there is a corresponding idea to F-map and C-map for relations, which we call R-map. And like F-map and C-map, that is automatically definable for a given type. And so then we can do a proof of the relational naturality based on the structure of the code for the given natural transformation. And this is just induction on all possible implementations of the natural transformation function. And then to get from the relational naturality law, which we have then proved, you want to prove the wedge law, which is a formulation that is closer to the purely functional version that we would like to work with. So that's basically an outline of what we want to do. And I think we can skip ahead here. A lot of the first few slides are basically summaries of ideas that we've seen a bunch of times in the book. I assume we all know have some idea of what parametric means. When Sergey says something that is fully parametric, or something that isn't. So if we skip ahead here to page.
One thing I want to make sure that I'm not crazy, right? Those last two examples are the same thing, right? Even though they have, one says some and the other says none. I think it's a typo, right? He meant to have a list of strings or something, or something that aren't ints.
There's a paren in a different place in the two examples. And so what does that?
Where
Right.
is?
So you'll
Which
notice
paren?
the first example, bad head opted listed to
Oh.
blah, 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 ends in two parentheses. Second one ends in just one. And I think
Looks like the first one's not well formed. Oh, no, I see, I guess. So the first one, you're mapping them to strings.
right, and then you're passing it to bad head opt.
Okay.
And
Versus the second one, you're passing a list of ints to bad head up.
right. And so the second one always returns, for a non-empty list, it always returns none. If it's a non-empty list of ints. If it's a non-empty list of anything else, then it behaves like a normal head opt. And so, yeah, so that
Okay.
the different behavior is what's expected.
Okay. Yeah. I missed that moving of the parenthesis.
It's not easy to spot.
Yeah. Okay. So where do you want me to go?
So here's a
Oh,
good place
yeah.
to start. So this is for those of us in the other track where we are frequently talking about the basic ways to construct terms in a language. This is the set of term formers in the language that Sergey is talking about. And so you've got the unit value, you've got variables, you have lambdas, you have application functions, you have the introduction and elimination of pairs, introduction and elimination of co-pairs, I guess co-products, and recursion. And those are basically all of the constructs that you find in a language like Haskell. This is sort of the stripped down core of a typical functional programming language, with the exception that you can combine products and co-products into more complex data types. In a typical functional programming language, but the sort of algebraic data type that you see in Haskell, for example, can always be factored out into products and co-products. So this is basically all you need to talk about how a functional programming language is put together.
A quick question.
Yes.
Could construction number 1, does that ever extend to other constants? Can you refer to the number 3, for example?
You can.
Well, okay, that's a bad example because you can get it by co-producting 3 units together, but
yes, and in fact, every well-behaved data type or value of a data type can be conceived of in terms of types that are constructed from products and co-products. There's basically, yeah.
I see. What about a string? How about the string foo? Can you
string? Well, in Haskell, strings are lists of characters, and
yes,
characters are, I think they're built in, but they're isomorphic to a type that
big
could
co-product.
Yes.
I see. Okay,
So,
so in theory, you could, in order to construct the, I don't know, the character whose code is 17, you could add together 17 unit values and let that stand in.
yes, or you could make a 17 element list of units.
Right. Okay.
So,
okay.
Yes, that's a little bit awkward if you actually want to represent them that way, but these are all of the pieces that you need to build up the types that you want to work with.
Cool, thank you.
Good question.
Yes.
Do you want me to go ahead?
Yes. So here's the naturality law. This is where we want to get to with all this. We want to be able to say, when you have a natural transformation T that takes you from one functor to another, or more generally also from one contrafunctor or profunctor, but the contrafunctor cases are all going to be similar, and the profunctor is basically a functor put together with a contrafunctor, and so it's basically the same thing twice, except one of them is backwards. So this is basically the thing we want to prove. So you have a natural transformation T, which goes from f of a to g of a. And if you do the f map from an f of a to f of b, and then do the natural transformation, you get to the same place as if you do the natural transformation first and get to a g of a, and then do an f map on g. So this is our goal. And
silly question here.
Yes.
I don't, maybe this is something that it's not legal to ask, but why it is needed for T to be a natural transformation? Where is naturality required here?
Well, the naturality ultimately is what we want to prove. So we're presuming that it's a natural transformation. We're presuming that it's natural. because it is going from one functor to another.
Yeah.
Um,
Okay.
And so what we want to show is, in the end, what we want to show is this square commuting is basically the definition of the naturality of T.
Okay.
So
Okay.
so that is what we want to prove. So yeah, I'm getting a little premature by calling T a natural transformation, but you know, secretly we know what that is what it is. So it is some function that goes from f of a to g of a, and it's defined in terms of the programming language constructs that we saw on the previous slide. So
it occurs to me that this doesn't really show the, you know, the fact that it's parametric in A. Like there's no A in here, but I guess the point is you can,
right. So this
all you can do with an A is, you know, use it in a function or something.
right. So we're dealing with a language in which terms and types are clearly separated. So this is the set of terms that we have to work with. So A is a type parameter, and I think there's another slide here which shows the set of, yes, it is on page 9. You have the list of the fully parametric type constructors. So this is the set of types that we have to use with. So you've got the unit type, you have type parameter, you have product types, coproduct types, function types, recursive types, and universally quantified types. And so that's the full set of types that describe that full set of terms from page 6.
Well, that's the full set of type constructors. Yeah. Yeah. So I guess T of A includes like, well, I was going to say the constant A, but you don't know what that is. So no, I guess not. Okay.
Right. T of A in this set of slides, it always refers to something of the type f of a to g of a for some f of g. So it's a mapping from one functor to another. But
okay.
But the f's and g's can only be built up from this set of type constructor primitives.
Right.
So let's see.
Right. So yeah, I guess I was just thinking. So if f of a is just a, then T of a is like some sort of function from a to g of a. And so you use the function, create a function number 3, and x will be of type A, right? And you can use x in that expression.
Right.
But that's all you know about x, is it's a variable. And you can use it, but okay. It's of the parametric type.
Yeah.
Yeah. Okay.
So let's see, we can maybe skip the Yoneda example. So this is just just some so Yoneda is I guess an example of why we would want parametricity. But
You can use parametricity to prove your data or establish it. Yeah.
but if we want to charge ahead towards the proof, then we probably want to go on to page 10. So where do we get the F map and G map for a given, or the F map rather, for a given functor like F or G in the F and G in the type of T, our alleged natural transformation? So it turns out that for a given functor built up from the constructs in our language, the definition of F map is completely determined by the type of the functor. And so this is the table basically that gives us how to build F map for any functor type. And so that's very convenient. We don't have to work with potentially different F maps or different C maps in the case of a contrafunctor. They're just we know what they are immediately by looking at the type.
Okay.
Right. So this
What down there, there's FMAT G1 and G2. Where did they come from? Oh, I see, because the recursion scheme is G, so you can define, yeah. Okay,
Right,
so you
and-
have FMAP
and
of
and
G, I
is a-
guess.
G is a functor, and so by the inductive assumption, we have the F map for all of the necessary functors.
So we have, well, it would give us FMAP of G. Oh, but you can parameterize G in either the first or second parameter, and that's why you have G1 and G2, I guess.
Right.
G1 would probably be
Yes.
if you parameterize in the first parameter.
Right, and either of those would be a functor. So we have an F map for each of them.
Okay. Any other questions?
And so the next page shows that C map can similarly be derived automatically. Just in case you were worried that the contravariant case was not similar to the covariant case.
Okay.
Now we have a slide about covariance and contravariance. I assume we are familiar with those. Then comes the question of, well, what happens if you have some sort of type constructor that is neither covariant nor contravariant? The word I've heard used for this is non-variant, since the word
That's much better.
invariant is already pretty heavily overloaded. If you want to have a word that is not confusable with invariant, you might want to call it non-variant. So a type constructor that has the same thing in both contravariant and covariant positions is not going to be contravariant or covariant. But what you can do is you can break out the two positions and fill them with different type variables and create a profunctor. And then you can put together the CMAP of the contravariant part and the FMAP of the covariant part and get XMAP for the profunctor. And then you can XMAP over a profunctor where both of the type arguments are the same and get something that functions like some analogously to FMAP or CMAP for the non-variant functor. So in this case, in the diagram at the bottom, you take a profunctor where both the co and contravariant arguments are A, and then you can do a CMAP, CMAP on one and FMAP of the other, or FMAP on one and CMAP on the other, and either one will be equivalent to XMAP as shown in the diagram.
And so XMAP takes a pair of functions, like FMAP would take one function, CMAP kind of takes one function, but kind of going in the other direction. And XMAP takes two functions, any two functions of that kind. And
right, one is in the co-direction, the other is in the contra-direction.
Right. Okay.
And so these are some
Antonio?
Yeah. Could we go back for the previous slide? Sorry, but okay, so CMAP is taking an XMAP is taking a couple of functions, right? But how? I'm not sure that I understand how the composition of CMAP with FMAP is possible if you are applying both of them to just one function, and you have a pair of function from which you are applying CMAP from one of the function from the pair, and the IFMAP to the other. So it shouldn't be.
Well, the CMAP is working on the contravariant part of the profunctor.
Should it be the map composed or a kind of product with the identity map or some doing and so and it's something where how at the end how do you form the application of a map for a couple of functions from the composition of application of maps for just one function? This should be.
Well, FMAP and CMAP each take just one function.
Yeah.
And they're combined using function composition.
Right, which you can see at the fifth bullet point there.
Okay.
That's
okay.
the definition of XMAP.
And then is composition.
Okay. So the one function is composed with the other. G is composed with F.
Right.
Right, and you are mapping the image of the first function, composing it with the image of the second one, and it is okay. So it is related through the function composition of G and F. Oh, okay, okay. I was
Right.
thinking a kind of product. Okay.
Right, and it's as you can see, it's commutative. You can do the CMAP and FMAP in either order.
Yeah.
Because they're operating on the separate co and contra parts of the profunctor.
Okay. Okay.
And they don't interfere. That's kind of.
But doesn't the composition of functions G and F change the order? Are these composition commutative?
Yes, in this case,
Okay.
yeah.
Okay. Okay.
It's like they're defined like above, the types are given. But then when you actually do the X map thing, it's on P of AA to P of BB. So you're actually, your X above is A and your Y above is B. And so it all kind of works out. I don't know if that made sense, but anyway.
Mm. Mm.
Okay.
Yeah,
Okay.
are we happy with this?
Yeah, I'm happy, more or less. Yeah.
So FMAP and CMAP satisfy two laws, which are very convenient. So FMAP of identity is identity. And when you lift F and G separately and compose them, that's the same as lifting F and G composed.
Right.
Mm. Mm.
So these look an awful lot like the definition of a category.
Mm.
Right.
So that's always satisfying. And so these are the proofs of those functor laws, which we can skip over for now if you want, since this is not on the direct path to the proof of the parametricity theorem. So this is basically just restating the previous section about functors and contrafunctors and profunctors and their FMAP, CMAP, or XMAP. They can always derive from a given F, we can always automatically derive the FMAP, CMAP, or XMAP, and the function will always be fully parametric and automatically lawful.
Okay.
Okay.
So here we start more on the main theorem. Of history.
Okay.
Yes. So here the top thing is that's basically what we're aiming to prove here for a given T.
But then you can't necessarily lift things into the functor if it's
Right.
not in the right form.
Yes, so it is easier to prove things for a more general form when we are not dealing with either functors or cofunctors, but arbitrary type constructors. And so the techniques here is, or the main technique is to generalize things to relations. And in order to do that for a given type constructor, we're going to want to define a relational version of the F map or C map or X map that we would find in a contrafunctor, functor, contrafunctor, or profunctor. And so that is the R map here. And so then we can come up with a different, more general formulation of the naturality law that we're looking for. And that is the one in the diagram here. And it says basically if you have an f of A and an f of B that are in the R map relation for F, then T will transform those into a G of A and G of B that are in the R map relation for G. For
Right.
for a given R.
And I guess the last point is that the relational one will reduce to the ordinary one when they're either both co or contravariant.
Right, and when R is actually the graph relation for a given function.
Right, right.
Yeah. And so
This is what he's saying.
right. So this is the ordinary function view at the top, and then the relation view, the more general relation view at the bottom.
Yeah, okay. And in the bottom one, if we replaced R by graph of F,
Yes.
then we basically get pretty much exactly the top one. Well, you'd have to change the arrows to be unidirectional, but
Right.
yeah.
Yes, but you know you can safely do that because the graph F relation, it is a function. F is a function, so the graph of it is it will never map a given input to more than one output, so it can be properly turned back into a function.
Okay.
So here we're just talking about relations and the notation for them. I assume none of this is really big news. It does mention the definition of a pullback here. So that is a relation where you have, if you have two different functions then two different arguments to those functions that map to the same output will be in the pullback of those two functions.
And he, I guess, partially includes it because it's not the graph of a function in either direction.
Right.
It's not the graph of a function.
So here are some combinators for relations that Sergey will be using in the proof. And so these are useful ways of thinking about things. So you've got the pair product relation, which is a relation between pairs, and it means that if so you've got two relations, and you've got basically pairs of things that are in each of the relations. If the how to put this? So if you have a pair from the first relation and a pair from the second relation, you can basically include them together and get a pair of pairs that is in the pair product relation, the two input relations.
Right.
So pair coproduct basically again, it's a relationship between two relations, and the right. So if you have a pair that is in the first relation, then we mark its components with a left in the sum relation, and if a pair is in the second relation, we mark it with a right in the sum relation. Finally, the pair function is a relation between two function types, where if yeah.
Did your sound cut out, or did I?
No, you are mute. You are not. You appears as being not mute, but we are not able to hear you.
Are you?
Now,
Oh, now
right,
we can.
Oh,
right.
okay, all right. So sorry. Okay, so
Function
have
map mappa. Right. It was at least I heard until the pair product it was audible, but when you were
okay.
right.
Okay, so the pair function relation, if you have an AB in R, then you have F of A and G of B are in S, then that means that F F comma G is in the function mapper relation between R and S. And so this is the diagram. Basically, it's a way of relating two functions if you have two relations between the inputs and the outputs of the functions.
So I have a question about the coproduct. It says if AB is in R or if XY is in it. Could it be in both? Could both AB be in R and XY in S, or is there some
It could
either
be,
that I'm missing?
it could be, but you have to choose one.
Or maybe not. Maybe you would have both left of A, left of B, and right of X, right
Yes.
of Y
Yeah.
in
Yes.
the sum.
Right. But you're always tagging you're always tagging it in such a way that you know which of the original relations it came from. It's very much like if you have an either AA, you have to, you still have to, A and A are the same, but you always have to say whether you took any given element from the left A or from the right A. And so the same is true here. If R and happen to be have the same type, you still have to say which one, if they have the same type and if they overlap, you still have to say which one you took it from.
Right. So this is sort of going to end up being a union where the first part has all the lefts from R and the second part of the union has all the rights,
Right.
labeling things from S.
Yes.
Yeah. Okay.
Yeah. And so the last one is reverse, which just inverts the direction of the relation, but doesn't do anything particularly interesting.
Right.
So armed with that, then we can define our map automatically for any given type constructor in the same way that we could define fmap automatically for a function. And so you can do that given the type expression, and you just follow these rules. So and the rules are expressed in terms of the operations that we just saw. The product sum function mapper combinators. And so as you, we don't necessarily have to do these in great detail, but as you would expect for a fixed type or a variable, RMAP is very simple. For a product type, you use the product combinator. For a sum type, you use the sum combinator. For a function type, you use the function combinator. For a recursive type, you actually have to do an RMAP 2, which is a 2 version or a 2 argument version of RMAP, which, as Sergey says at the bottom, we will define in a similar way. And you also need that for the universally quantified type. And Sergey specifies at the bottom, the inductive assumption is that all of the subtypes that you're building this type up from already have the RMAPs defined. And so inductively, you could just build this up in a straightforward way. So I didn't actually try to, let's see. Oh, no, I take it back. Next page is where we are looking at RMAP 2.
Just before we leave this, I was wondering, like in the universally quantified type where we have for all X and Y, I mean, RMAP F of R is supposed to be a set of pairs, but then on the right-hand side, we have for all. I'm wondering if that sort of ends up being sort of like an intersection. Because what we really want at the end is a set, right? A set of pairs. Do you know what I'm saying? I'm not sure. Okay, well, we can go on.
Right. So the more complicated cases from the previous page require simultaneous liftings. And so here, Sergey gives us the definition of RMAP 2, which gives us that simultaneous lifting once again by recursing over the possible structure of a type. So I didn't actually look at this in any detail, but it looks plausible to me, except that when you get down to the recursive type example and the universally quantified type, you realize that you in fact need an RMAP 3 as well. And so that can be defined analogously. For any given F, you will only need a finite number of these RMAPs, but you do have to sort of assume that they are that all of the RMAP ends that you need have already been defined in order to do it.
They just follow the same pattern, presumably. And
Presumably, yes.
yeah, I wonder if a dependent language we could just define them, but in terms of a NAT or something. But anyway. Yeah. And so the point is any particular F has a finite structure. So it might have recursion and universally quantified things in it, but it can only have a finite number of those. And so you're going to go out to some RMAP K forever, how many of those there are.
Yes.
Yeah.
So,
Did we already do this?
yeah,
No.
this is the previous page. So this is our
Oh,
map.
did I go the wrong way? That's
I'm at
the
one,
problem.
yes, I'm at two. So
Oh, yeah.
here are some examples of defining our map. And so, right, these next three pages here are examples for various type constructors. We want to rush forward into the proof. I guess we don't have to look at those because we'll just assume that they work.
Stop here or keep going?
Yeah, so
So T now is not a function anymore between functors.
yes, it is. If you look at the type, you can see it's not a relation. It's still a
Oh, I see. Yeah.
function. But I don't think we are requiring that P and Q be functors. I think they're arbitrary type constructors.
Okay, so yeah, on the next line where it says fully parametric, T of A is in F of A. I guess implicitly F is, or F of A is P of A to Q of A. Is that right? Or is F just an arbitrary functor in that first bullet?
I think F is an arbitrary type constructor,
Okay,
not necessarily co or contrary.
okay. Right, so he's saying instead of doing that, do this, okay.
Right.
So T is not necessarily a function then, right? It's just a value, a
I think
polymorphic value in F of A.
yes. Right. And so here we are going to use free variables sort of without restriction in the proof. And this is a valid thing to do. If you have a variable that is not bound to anything, you can basically just use the variable symbol in proof and it will stand for any arbitrary value of the relevant type. And so you can right. Here we do seem to be assuming that T is a function because you can apply it to C.
Right. 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 Okay.
So right. So we assume that some term T that is parametric in a Z as well as in the type A we assume that that satisfies the relation of naturality law. So that is the inductive assumption. And then depending on the structure of T, or sorry, that's the goal that we are trying to prove, but we assume that each of the sub expressions in T inductively satisfies the naturality law. And so we can do a proof by cases on the 9 possible forms that T could have.
I guess that would be this.
And so here are the first 4 cases of the proof. These are relatively easy cases.
So here C is a fixed type, not necessarily, yeah, could be nat or, and anything.
Right,
Doesn't have to be a variable, type variable.
right.
Yeah.
So T is just a constant function, and R map gives us the identity, and C comma C is in the identity. So the second case is the case where the body of T is just the variable Z. And so right, and so by the definition of R map, we can pretty much immediately see that Z1 and Z2 have the R mapped relationship whenever Z1 and Z2 have
So do you think the first Z1, Z2 are in R instead of R map P of R?
yeah, right. How does that make?
Where Z and T of A have type P of A.
Yeah.
Okay, so maybe it's right the way it is. I just kind of got thrown because in both cases,
Right.
you're defining the type R map P of R. You're sort of defining R map P of R recursively in terms of itself, I guess.
Yes. Yeah, that's
Okay, well, I'll let it go.
right. Because all of the other cases are phrased similarly. So the next case is a lambda. And so the lambda will always have the form where the body is some function of the outer parameter Z and the inner parameter H. And so the thing we need to prove here turns out to be just the same as the inductive assumption for S of Z and H.
Yeah, okay.
So the use function or application is basically basically you're applying some G to some H where the parameter to Z could appear in either Z or H.
Can you always decompose a
Yes, you
function
can.
like that?
Right, because the offer, yes. Any
Make
term
one
that has a Z,
PID.
right, any term that has a Z in it can be viewed as a function of Z.
But can you decompose it into that G of Z
Well,
applied to H of Z?
right, specifically, we are looking at application. So this is the application case. So we know that
Oh, got it.
the body of T must have the form of an application. So G and H rather can be anything that may contain Z.
Right. So those are the
Yeah.
inductively generated subcomponents. Okay.
Right. And so the inductive assumptions for G and H give us the answer that we are looking for T. So then we have the tuple case. So in this case, we have the body of T is a pair, and the subterms are U and V. And again, U and V could each contain the variable Z. And so we view them as functions, U of Z and V of Z. And the RMAP for this case uses the P-prod relation. And so we take the definition of that relation on the inductive assumption, and that gives us the necessary answer. And so then we have the projection case. Uh, and we use the inductive assumption on the the-
Adrian, we lost some sound. Right?
Yes. Okay, can you hear me now?
Yes.
Right. Yeah, some of it is just because I'm hesitating because this is complicated enough that I'm having trouble following. But basically, again, we use the inductive assumption on we've got
Yeah.
some G here is some term with the form of a product. And so you have an inductive assumption on that. And you can project out the components of G that gives you the desired conclusion for
Right. The
T.
T-prod basically takes things from the first thing, which are map Q, and then pairs them with things from the other side. So when you project out, like the first component, you're just getting the on map
Right.
Q guys.
Yes, just the Q's. And similarly for the second component. The next case is the coproduct case. Where you have you are creating a left from some term G, which is again a function of C. And so you have the inductive assumption on G, which you can use to derive.
Just wrap them in lefts.
Yeah, you wrap them in lefts. And I believe the next line is a typo. I believe he wanted to say that the other case is right, not left, because we've already done left. In fact, in the lectures, he does correct that. So that is supposed to be a right, not a left. So finally, the cases are getting a little more complicated here. I think in case 8, he could have left out the S because any pattern match on an arbitrary term like this can be decomposed into a pattern match on a simple variable and an application of the pattern match to a more complicated expression. So I think the S here is redundant, but throwing it in doesn't give you something incorrect. It just means you're proving slightly more than you actually have to. So, when you do the pattern match here, the result for the left side is going to be some term that depends on both z and the thing that's in the left side, which is x. And similarly, the case for right will have the general form where it's a term that depends on both z and the thing that was in the right, which is y. So inductively, we are assuming that these terms s and u and z all satisfy the required law. And so yes, these terms are kind of complicated, but I guess it all works out. And so the left,
I'm
the right,
confused where P came from.
yeah,
Is P set S of A, because S is defined in terms of G and H. Oh, I don't know. Where did P come from? Maybe S of Z is in P? No, it's in S.
right. So we're assuming that the z's are p's.
Okay,
We don't.
P must be
We don't.
more globally defined.
Well, we don't previously have a type for z, so we can just give it a name.
Okay.
We see. UFC takes a G of n, gives us a Q of n. Right.
Q of A is the outer value, I guess.
Right. Q of A, and then that would have to be a function of x's type, which is a G of A. Um,
Mhm.
guess I don't quite follow. Yeah, I'd probably have to write it out to convince myself that I knew where all these types are really coming from.
Yeah.
But let's assume that something like this is correct. So for case 9, I think this, I think that might not be phrased quite right, because the general case of a recursive call, the argument to the recursive call will not be the same as the parameter to the outer call. So I think you want to say that the case here is T of Z equals F of Z of T of G of Z, where G of Z is some function that if this call terminates, will give you a thing that is smaller than the Z, than its input. Because otherwise this looks as if the recursive call always has the form of an infinite loop. And that's not the only case that you're interested in. However, I would assume that because the G also obeys the inductive assumption, that the proof wouldn't actually be complicated very much by that. So,
So G would also be Q of A to Q of A. Or what is Z here?
Z would be, let's see, what is
Q of A.
whatever Z's type is, it would be that to that.
Okay.
Yeah, it would be a thing that you would hope would give you a smaller Z, as it were. Something smaller than Z, but of the same type.
And so inductively you use the use function rule and you get the right stuff, presumably.
Right. So anyway, up to our confusion at actually following the code for each of the cases of the proof, that is the proof of the relational naturality law. And so once you have the relational naturality law, you'd like to rephrase it in a less relational way, so that it is more useful. And so the way to approach that is to use this wedge law. And so the wedge law is phrased in terms of a function, which is what we would usually be working with in practice.
Right. And P is a profunctor here. Right, okay. So T is just a function without free variables, but it is a function operating on polymorphically on A
Right.
and yielding. Oh no, wait, it's not actually a function, it's just polymorphic
It's,
in
yeah,
A.
a term.
Right. Because A is in square brackets, so it's not a function from A, it's polymorphic in A. Yeah. Okay. That looks familiar. I think, yeah, it is related to category theory, and I guess it must be ends where you have your profunctor and you define it on this whole space, but then you're mainly concerned on just what's on the diagonal. But because it has all the right relations, it has this nice property.
Right.
So where's X map is C map, and then F map P. Oh, Sergey.
Hello, guys. Hi. Sorry, I was not available. Sorry, I didn't want to interrupt. Hello.
Hello.
So I was just wondering, in this diagram, does one of those arrows go the other way?
No.
No, okay.
So, thing is that the PAA and PBB is actually the same term P that is applied to different types.
Mhm.
So you take a term which I denote by T, lowercase t, and so T of A, T is a function of type, right? So T of A is a value of type P of AA. But it's the same term, T, right? So the two, it's a bit of a weird diagram because usually diagrams start from one node of the graph, right, and then go somewhere.
Mm-hmm.
But in this case, well, you can draw it maybe in a different way, but the wedge is just that you begin with the term T and you apply it to type A, and you apply it to type B.
Mm-hmm.
And then you apply the lifting functions, the F map and C map, with different type parameters. And then you should get the same value. So the value is kind of a mixed type. This is not diagonal anymore. It's a profunctor P with AB. So it's a weird value which you don't necessarily need in any way. But anyway, this law is kind of a very general naturality law, where you have type constructors that are not necessarily covariant or contravariant, and yet so the point of this entire technique is that we have found some relational law for t, and we want to derive an equation. Right, so how do we derive an equation from a relational law? Well, we need to substitute functions in some way. So the first step is to get the wedge law, and that's very general. So that will work for any type constructor. That is kind of a generalization of the neutrality law for type constructors that are neither covariant nor contravariant. And I found in this blog post that I'm linking here by Bartosz Milewski, found a very kind of straightforward proof that the wedge law follows from the relational law. And that's what I'm using. So yeah.
So could I ask a question here?
Yeah.
You have this expressed via X map of FG equals C map P, and then F map. So that's why I was kind of thinking the arrow would go the other way, because you'd be kind of coming down to PAB and then going back up to PAA if it's and then.
No, but that's the X map has nothing to do with this diagram.
Oh, okay.
So
Okay.
if you wanted to define X map, you would draw a different diagram. Then you would draw a diagram like you're saying. You begin with some P, then you do a C map, and then you do an F map. That will be a different diagram. So
okay.
All I'm saying here is that C map and F map are related to X map, and so you could
get them out.
You could just use X map to formulate this wedge law. You don't and they don't need to assume commutativity law for X map to formulate that, which is important because commutativity law is a consequence of parametricity. You don't want to assume parametricity in order to prove that law. So
parametricity.
you want to kind of dependence-free proof. We have found parametricity. Now you want to prove the first equation that follows from it, and you don't want to assume any other equations. Just anyway, but maybe this is too much digression. So if F map and C map is good for your understanding, then you just keep them, because F map changes one type parameter and C map changes the other type parameter, and that's what we need in this diagram. So maybe this entire consideration about X map doesn't actually elucidate or clarify anything. I don't know. But in any case, it's important that we do not use the assumption of commutativity. Now, commutativity assumption means that if you F map, you change one type parameter. If you C map, you change another type parameter, and you can do this in either order, and the result will be the same. But this can be derived also from parametricity, but we don't. Anyway, this is let me just
okay. Do you do that here?
I don't think I don't know if I derive.
You do it for X map.
Yes.
Yeah.
Yes. So I have a relational neutrality law for X map, right? Right. So I actually do that for X map because that's kind of a general law, and so yeah, I do actually go through XMAP. And so then the question is how to substitute parameters correctly. And so this shows you with which choices of parameters and which assumptions you have to substitute into the parametricity and the relational neutrality law. And then you get the equation. And I also show also other things that you need. So anyway, all the things that are technical that you need to prove. And then it turns out that if you have a type signature like G of A to H of A, where both G and H are covariant, then from the wedge law, you derive directly the neutrality law.
The regular
So,
neutrality
yeah,
law
just
for
regular
covariant.
Yes, yes.
Yeah.
Yes. So, so the wedge law is a generalization of that, and so once you derive the wedge law, you're kind of done. That's kind of a master equation that gives you all neutrality laws.
Okay.
I'll let you drive again. I'm sorry, I didn't want to derail your discussion.
Right, you would make a much better driver than any of us, but yes.
I haven't looked at this, so I can't talk. I can't.
Right.
You have what? Sorry, what did you say, Peter?
I'm sorry. I didn't look at this slide, so I don't
Okay,
think I could
okay.
drive
Yeah,
it.
I kind of
but-
skimmed over everything after the naturality law and the wedge law.
Mhm. Okay, well, let me then, we'll have 10 minutes, so I can just finish this. So now that we have found, we have proved everything, modulo some technical lemmas that I did not prove in the slides, but they are like the identity extension lemma of Reynolds. It is, it needs to be proved in some form also, which you can do. So what I wanted to show is some applications that that go beyond using UNIDA. Now UNIDA is a shortcut, which is essentially neutrality law. So if you have some type signature, which is then a natural transformation, then you can sometimes use UNIDA to simplify that. But so I wanted to show applications where I simplify certain types to which UNIDA identities do not apply, because the type signatures are more complicated. So one example here is that you have this type for all A, from function A to A, you get either A, where E is a free type variable, so it's a fixed type. So UNIDA identities do not apply here, and this is not a natural transformation. This is neither covariant nor contravariant. So kind of nothing works in the usual. The wedge law, of course, it holds, but it's not enough actually to simplify this type. So you can write down the wedge law, it can give you some equation, and you don't know what to do then with that equation. And so here I show what you can do. You can, so first I formulate what is the relational neutrality law, which is that for any functions k and l, if kl is in a relation, then p of k, q of l is in another relation. So this is kind of, again, you kind of write it down, don't really know what to do with that law. You have to somehow get some kind of simplification. So what kind of relation R? So now you see the relation R is arbitrary in this law. Right, so for example here, you use R. Now R is an arbitrary relation. It's completely arbitrary. You don't, right? You don't know what that should be. Right. So then the question is, okay, well, what can I do with that? Sorry, this is something I didn't want to do. So which relation? Now, in this case, this is a specific technique which works in this particular example, is to use this empty relation. Right? So empty relation is a relation that never holds. So no values are in that relation. And it's like an empty function, right? So except that the types A and B are not void, but no values are in that relation. So that's kind of, it's not a function from A to B of any kind, or not a function from B to A. So it's really just a relation that you choose because it works in this example. So what happens then when you substitute this empty relation into the relation neutrality law, and you get a relation that values of this type will satisfy? Well, what is that relation? Now let's calculate what that relation is. Well, it turns out that essentially all functions. So first you have to use this lifting, the function pair. You find that all KL are in that relation.
Because the AB is in empty, so basically it's a null.
Yeah, so it's an empty
Hypothesis,
empty premise,
Yeah.
right? Which is always false. And so from the premise that's always false follows everything. So right, so then for any functions k and l, right, then you have p of k, q of l in this relation, right? Now let's compute that relation. Now the sum combinator, the relation coproduct, means that either they're both on the left or they're both on the right. Now they cannot be both on the right because then you would need to satisfy an empty relation, which you cannot. And so there must be both on the left. And so it means that P and Q must be actually constant functions that for all K and L return the same value, which is on the left. Because I can say, well, what is P of K? It's some left of E. Now I can vary L, right? And for all L, it must be still the same. And so Q must be a constant function that returns the left of E for all L. And similarly, P of K must be a constant function that returns the same left of E. So there's actually one value of type E, which is returned here. So P of K and Q of L. So P is a value of this type, right? P is a value of this type where you apply this to type A. But Q is a value of this type which you apply to type B, and they should be constant functions that ignore this argument. This argument needs to be ignored, and then you return always a constant value left of E. And so that is
For
equivalent
some
to
E, I see.
yes, for some arbitrary chosen E. So then that means it's a constant E, which is arbitrarily chosen, and that's a type E. So the type E is equivalent to this type. So that's the proof. So you
What I
use
would have expected somehow, but
yeah, well,
that's cool.
This is your intuition, right? You cannot really use this argument to do anything.
Hmm.
You cannot call that function with any argument because you don't have any values of type A. So you wouldn't possibly be able to return the right part of this. And if you return the left part, then you should return a constant, because there's no way to use that argument. But you have to prove. So you prove that. You know, this is a proof. This is a rigorous derivation, which is not just intuition. You know, I can't use something, but actually, if you have a value that needs to satisfy that relational law, and then you substitute specific relations into it, and you get your specific result. So that's how it goes. We don't have time to go to the end, I guess.
Right, I guess
We're out of time, but
sort of out of time now, actually.
I had time. I would have a bit of time, but we have still too much to go through. We can go very quickly over this. The church encoding. So there are two more examples: the church encoding, and then there is another weird type that is again simplified. The church encoding is practically maybe more important. It tells you that an arbitrary recursive type, which is a least fixed point, which is least fixed point defined like this, is equivalent to this kind of type. Now that kind of type is not recursively defined. It is just a type with some type quantifier. So there's no recursion there. And yet that type CT, which is church encoded T, that's equivalent to the least fixed point of that type equation. T equals S of T. So in order to prove that, you need to prove a lot of things, actually. It's quite a long derivation. Essentially, you need to prove that there exist functions fix and unfix, which are inverses to each other. So this proves that for this, you need to, like S of CT into CT and CT into S of CT, right? So you need to write the code for those functions. And then you need to prove that this is a least fixed point, which means for any other fixed point, you have a fixed point morphism. And the fixed point morphism means that it's an algebra morphism and the co-algebra morphism at the same time. From CT into that other fixed point. So that's what you have to prove. Now, how do you prove that? And there is a unique such morphism, right? So because the least fixed point is the initial object in the category of all fixed points, whose morphisms are fixed point morphisms. I hope you follow what I'm saying.
Mostly.
But we can continue next time if there's interest. But essentially, this is so essentially what you need to prove a bunch of properties for fixed and unfixed, and you need to prove that using parametricity. You have to assume that this function, so all values of this type, are fully parametric. So and note that this type is not covariant, is not a natural transformation, neither covariant nor contravariant. So this is, again, something to which UNIDA does not apply. So it's not easy. You need to write down the relational law for values of this type and then derive properties from that. And then you can, using that, you can derive various properties of fixed and unfixed. Because fixed will be specific code, so you have to derive equations for that. And so anyway, this is how it goes.
You also have to define fold, I guess.
Well, fold is
just the standard fold.
Fold is identity function on this type. You need to define. I mean, essentially, fold is a function from CT to this. It's identity function. You need to show that this function has certain properties. You need to show that this function, for example, is an S algebra morphism and also an S coalgebra morphism, and so on. And you need to show that there's a unique morphism from CT to any other fixed point, well, it's enough to show that there's a unique morphism from CT to any other S algebra. So that is not easy. That's a kind of equation. Then you have to show that there's a unique. So any other S algebra morphism from CT to some S algebra will be equal to the application of this, which is not obvious to prove. And so anyway, you need to use parametricity several times in that proof. But this is an important application.
In category theory, is this related to, what is it, like Lembeck's law?
I'm not sure, actually. So the one problem that I have with this is that in category theory, the church encoding is not easy to represent. Because you have this complicated type signature. It's not a natural transformation. It's not a morphism. Right, so this CT, what is that object in category theory? It's not obvious. Hey, see you later. Right, so it's not obvious how you translate this into some statements about category theory. So well, I'm not sure what Lembeck's lemma is really, but so one thing that I can say is that so you need to consider the category of all fixed points of a given covariant endofunctor S. So you fix a covariant endofunctor S, and you consider all fixed points. And there are objects, and morphisms are fixed point morphisms. So morphisms must preserve the structure of the induction. So must be both algebra and coalgebra morphisms from T to T prime, say. So now that is a category, and then you can ask what is the initial object and what is the terminal object in that category. And the initial object is called the least fixed point, and the terminal object is called the greatest fixed point. And then you can ask, well, can I encode? Can I have a type that is the least fixed point or the greatest fixed point. And church encoding gives you the least fixed point in the way that I just showed. And you can also have a greatest fixed point, which is encoded like this. Which is kind of weird, but that's how it is. So this is, again, the existential quantifier can be encoded through the universal quantifier. So in principle, if you have the universal quantifier, then you can encode both the least fixed point and the greatest fixed point. But then you have to prove all of that. So you have to prove that they're actually the fixed points. You have to prove that they're actually the least and the greatest fixed points. So that is quite some work. There is a paper, I'm not sure if I linked it here, by Woodler called Recursive Types for Free. And you can, and this paper is not published, it's available only in plain text format with ASCII formatted graphics, diagrams, which is kind of weird. But anyway, so that paper gives some hints about how to prove the encoding that I just showed. Doesn't give the entire details, the full details, but it does give some hints about proving the church encoding and the dual, the greatest fixed point encoding.
Okay.
Anyway, I think we should wrap it up. There's the last example in my lecture is a type that is more complicated, like this, a third order function. And I proved this using some tricks, but essentially you can simplify this to just option K. Now this option is a technical device. It doesn't have to be option K. It could be just type K. But at the time when I was writing this tutorial, I did not have a proof that was easy for arbitrary K. So option K is a type where we know it's inhabited. And if you put K in here instead of option K, you have to treat this the case when K is not inhabited, when it's void. And I did not have a proof that was uniform. At this point I do, but it doesn't matter. So anyway, this is a type equivalence that is not easy to get. And that's actually, again, so this is an example where you have to use in a non-trivial way the relational law. The wedge law is not enough. You can apply the wedge law to this, but it's not enough. And actually, if you look at this type signature, this one is a covariant functor in A. So this is actually a natural transformation of the type so f of A to A, where f is covariant in A. It's positive. It's not strictly positive, but it's positive. So in principle, this is just a natural transformation from f of A to A. It has a neutrality law. So you can write that law, but it won't be enough to derive a type equivalence, turns out. So we need to dig deeper into the parametricity law and the relational parametricity law to get more information. So this isn't, to me, this is maybe an artificial example, but this is an example. First of all, it shows you that church encoding does not apply to contravariant. Well, church encoding gives you nothing good for contravariant functors. And secondly, it shows you that the natural transformations do not give you enough information when you want to derive properties of some types. Anyway, I need to get wrapped up.
Okay.
We're out of time anyway.
Okay.
Yeah.
So what do we want to do for next time? We can,
He was proposing some other paper that we can do.
Yeah.
together.
we can move on to that and assume that we have a sufficient understanding of parametricity. Unless we want to go back over the points that confused us this time. But sounds
Yeah,
as if
okay.
we are ready to move on, is that right?
Yeah.
All right, that's one yeah and no objections. So yeah, let's go ahead and read that paper that Hugh proposed. And let's see, 2 weeks from today would be the 7th of September. Is that good for people?
Yeah.
All right. So composing monads using coproducts. Let's do it.
All right.
All right. See
Talk
you
to
all
you
in
later.
2 weeks.
Thank you. Ciao.
Thanks, everyone.
Okay.
Bye.
Bye.